Okay. So today what we plan to do is the following. We want to do some basic Fourier analysis, see, and prove something for the L1 theory. And for L2, so the Fourier analysis gives a map, which is actually a linear map on a Banach space, on Banach space L1 or a Hilbert space L2. And in Hilbert space, it's a unitary. It preserves norm, it preserves inner product. On L1, it's not a nice map. It's not unitary. In fact, it will not map it onto some Banach space or something. It will just take it into this Banach space C0. I mean, this is L1 of R, this is C0 of R. Function vanishing at infinity. It is those functions. So here I have done. So first we will consider the L1 theory, then we will do the L2 theory. Possibly today, or we may take one more class for this. Okay. So as a side remark, I will say something about the discrete case also. So we are assuming by L1, L2, we mean L1 of R. So before that, let's understand what is this Fourier analysis. Fourier analysis is something you have a group, okay, here in this case R, or you can take, you take the interval 0 to 2 pi means this is isomorphic to circle. This is circle basically. You take the circle, then you consider the homomorphisms of from R to the circle. Okay, circle is Z such that mod Z equal to 1. The complex plane. You take the homomorphism. So in this case, it's all given by natural numbers. Integers. E power INX. Okay. This is for each n, this will be a homomorphism. But in this case, it is given by IXY. I mean, y going to IXY. Here, x going to INX. In the circle case. So a Fourier analysis, you take a group. I mean, in harmonic analysis or something. You have a function here. You have a function on this. Then you want to get a function on this. G hat is the all homomorphism. I mean, you assume G is an abelian group. If it is not abelian, then it's a different thing. Then you will have F hat on this G hat. So the idea is the F hat will, I mean, when you want to study this F or the collection of F, collection of functions, by studying this F hat. Okay, so that is what this harmonic analysis, all these things about. Okay. So here in our case, so that's why when you take circle, when you take the interval 0 to 2 pi, when you take the interval 0 to 2 pi, then the Fourier series is a function of integer. So if you have a Fn, you have a Fn L2 of 0 to 2 pi, or you can take any interval. You have to normalize the Fourier transform. Then F hat, so F is from here to C. I mean, it's taking values in complex numbers. Then F hat is a function from integer to complex number, of course. Okay. There is no reason for, I mean, I have said unnecessarily I have said L2. There is nothing like L2. It's a function on this. It's just I mean, for the time, it's usually a L1 function or something. Okay. L1 function. So then F hat is a function. It's a number. It's a discrete number. On the other hand, if you have a F in L1 of R, then you have an F hat, which is on R. I mean, the dual of, see, here I'm using the R both the places, but the homomorphism is actually given by, I mean, for each Y, for each X, you have a homomorphism there. Okay. So anyway, forget about all that. I mean, that is just the idea of our general harmonic analysis, how you do. So the idea is, if you have a, so maybe I will erase these things. So definition of Fourier transform. I will make both the definition. If you have a F in F in L1 of R, okay, then define the Fourier transform F hat at some xi equal to integral over R f of x e power minus I x xi dx, okay, for all xi in R. So you have a function on the real line, then you get a function on the real line. Instead, if you have a function on the interval, then you will define it as a natural number. For if you have a, I mean, this is the discrete Fourier transform, discrete version. If you have a function in L1 of some interval 0 to pi, then f hat of n for n in z equal to again the integral f of t e power int dt. Okay. So this is the discrete version. We are going to study the continuous version that for the whole real line. That's what we want to study with this. Okay. So this is the definition I have made. So as you know, as you can see that this f going to, so the property one is f going to f hat is linear. That is clear. Okay, if you multiply an f by alpha, a scalar alpha, then alpha can be taken out. If you have f1 plus, because integral is linear, this is also linear. F1 plus f2 is linear. So a Fourier transform is linear. Okay. So the second property is, so if we take a conjugate, if we take f bar is a function, okay, then f bar of hat equal to, you will get f bar here, but then integral is integral is like summation. If we just think about it, integral, even if it is Riemann integral or Lebesgue integral, whatever, it is like a summation. It's like you take a simple function and you just sum it by sum the scalar. So the bar can be taken out. So if you have a bar here, then you can put the bar here with a plus sign here. Then you can take the bar out, okay, out of the interval. So let me not write it. Those things will imply that f hat at xi equal to f of minus xi bar. F hat. So the f hat, the bar hat of f bar is f bar minus I bar. Okay, that is just clear. You just substitute it, you will get this. Okay. Then this is a nice map. It's a bounded map. Okay. You consider this f xi mod, which is equal to mod of integral over r. So I am just doing it for the continuous case. The same thing will follow in the discrete case also. Okay. In these things, there is no difference. Okay. So integral over r f of x e power minus I x xi dx modulus. So that is less than or equal to integral of. So the e power ix, that has modulus 1. So that will just go away. It is just f of x dx. So which is norm f1, the L1 norm this. So f hat xi is less than or equal to f1 for all xi. Okay. So I will do something more. So after that, I will make the statement. So this says that f hat xi is bounded uniformly by this norm f1. It's bounded, but it's bounded. F hat is bounded. Okay? This implies f hat is bounded. I want to say that f hat is also continuous. That's the next one, I believe. Yeah. So f hat is bounded. The fourth one is f hat is uniformly continuous. So why is that true? So we want to f hat of xi plus eta minus f hat of xi. Okay. To consider this, so that is equal to, just write the, maybe I will take the modulus also inside with the smaller than or equal sign, is less than or equal to integral of over r. So here we will have f of x, and here we will have minus I xi plus eta. So we will have the modulus here. Minus e power I xi x, right? This is what we have. Now we can take e power I is ix out from this modular, the second integrand, the second product of the second factor of the integrand. So which is modulus 1. So this is equal to integral over r mod f of x modulus of e power I psi eta x minus 1 dx. Okay. Now as you can see, this is just eta. We have taken e power I is ix out, so this is eta. I eta x. Okay. There is no xi on the right hand side. Okay. There is no xi on the right hand side. So, I mean, then it's given, you can talk about when when this eta is in some nice interval, then this will, this implies, I am sure you know all these things. Also, notice that this thing converges to 0 as eta goes to 0, right? Eta goes to 0, this goes to 1, and so this goes to 0. That factor goes to 0. So, and there is no xi on the right hand side. So this implies f hat is uniformly continuous. I believe this uniform continuity is clear. Okay. You can choose a uniform delta given epsilon. You can choose a uniform delta such that this thing is less than epsilon. Okay. So that's what uniform continuity is. So these things imply that we have so this f is in, so this implies f is in L1. That's what we have defined it for. Then f hat is in C of R. We will prove that it is in C0 of R, which is a Banach space. So this is not a Banach space. All continuous functions is not a Banach space. F hat is C of R, but it's still a vector space. We will come back to that. So, and we know that, okay, we want to take the supreme one. Okay, we will talk about the L infinity now also. We will do the infinity now. We will come back to that. So fifth one. So next we want to talk about derivatives. So these things I should leave it as exercise. You can actually consider many things. Like for example, you can consider a new function f of x equal to, if f is in L1. Whenever I say L1, it is L1 of R. So then you can define minus infinity to x f of x dx. You consider this function. Suppose this f is also, if f is also in L1, then you can compute the f hat. Okay? Then you can compute the f hat, and I think that will be, I think f hat will be something like f hat will be, so you will have a f hat of xi will be, okay. This is just easy. You just have to write the definition and you will get this. Okay. So this is exercise. The next exercise is, or you can write it as, if you have two functions, f and f prime, both are in L1, then f hat of xi equal to I xi. I think there is I xi of f hat of xi. F prime hat of xi equal to maybe A, B, A, B, C. If you have a f is in L1, you have a f is in L1, and you have x f of x. If you multiply by x, that's also in L1. Okay. Then, so I will prove C because I will need it. The other two, I leave it as exercise. I mean, these two are same. A and B are same. Okay. So then f hat is differentiable, and f hat prime df by dz equal to, so it has to do something with that. So which is IEX f of x. This thing, whole thing hat. See, proof of C. So you have to consider this f hat of, you want to differentiate f hat. So f hat of xi plus h minus f of xi divided by h. This is what you want to consider. And that is equal to, you just write the definition, which is f of x into e power minus I xi plus h minus e power minus I xi x. Right? Okay. So now notice that this, the integrand. So what do we want to do? We want to consider that, we want to say that this converges to something. So this is just, consider this e power I xi plus eta xi plus h, no? H, xi plus h x minus e power, there is a minus here, yeah, minus I xi x. Okay. This modulus is equal to, you can take e power I xi x out, okay? Then you get e power minus I hx minus 1 by h. So the point is, this is less than or equal to x mod x. This is right. So why is this true? So e power I hx minus 1, which is yeah. So you want to take the modulus of that. So modulus of that will be, you take the modulus square, e power. So I will do it once, maybe we'll repeat this again. Minus 1 modulus square by h square. This is equal to, so e power I, so cos, so we'll get a cos hx, we'll get cos x hx square, no? Cos h square, the real part of that, minus 2 divided by h square. Is that right? Now this sin hx by 2, I mean, this is less than or equal to, is there a 2 factor coming somewhere? Sin hx by 2. And this is less than or equal to h squared. This is okay. I seem to miss a factor of 2, but somewhere missing. Anyway, the point is, whatever the integrand we have, just check it. Okay, this is how one do it. One does it. So there is this integrand, which is this integrand. This is bounded by mod x f of x. I mean, this whole integrand is bounded by mod x f of x, and we have assumed that this x f of x is in L1. Okay. Because of that, you can take the limit, and you can take the limit inside. You can apply dominated convergence theorem, and you can take it inside. So once you differentiate it, this e power I, this thing, I mean, e power, oh, I have missed a by h here. I missed a by h here. So this thing, when you differentiate it, you get ix out. Okay. So it will be, so the rest is exercise. Okay. Is this clear? You just have to take the differentiate sign in, I mean, differentiation inside, and you have to differentiate this. You have to differentiate with respect to, I mean, h is it's a function of xi, and it's varying here. So, and you will get I xi x. You get no, you get I. What do you get? You, if you differentiate with respect to, no, you will no, yeah, you will get ix. Okay, because that is where you will get ix out, and that's what we are getting here. No, you will get ix will not. You will get I xi. The h is with the x, so that will go away. Anyway, yeah.
That's like, can you explain this part again? So, so you are bounding e to the power minus I xi plus h of x minus e to the power minus I xi x by h by x square or x?
It should be x square, correct. It should be x square. That's because sin x by x, that's a nice function, no? That is the, I mean, that is less than or equal to mod of this is less than or equal to norm x, mod x. I mean, near 0, it is behaves like mod x. Otherwise, it's less than or equal to 1. I mean, it's less than or mod x.
Okay? Near 0, near 0 sin x
without
goes to
this,
1.
Without this, that's why I'm saying without this. Sorry, sorry. This is what I said. Sin x is less than or equal to mod x. This is what I said. Okay, they're not there. That's what we are using. We get hx by this, but I'm somehow missing a factor of 2 somewhere. Oh, there is it will be 4. Sorry. This will be 2 sin square. No, there will be 4. Correct. That's okay. Now it's okay. That's what I said. There is a mistake. Now it's everything is fine. I have 4 here. Okay. This is 2 sin. I mean, this thing is 2 sin square hx by 2. No. Sin square or sin x?
Sin square.
Okay. Whatever. You should know better. Okay. Finally, we should get the answer. You should differentiate. This is an easy exercise in calculus. I don't want to spend time on this, but it should be okay. It should be clear. Okay. Okay. So that is about differentiation. Yeah.
Just one more thing, sir. So there. So can you repeat what you did after like bounding that quantity by?
After bounding this, so what I have done? Where is it? It's here. So after bounding it, you take the limit h going to 0. You have to take limit h going to 0. So you are up. This whole thing is bounded by x f of x, which does not depend on h, which is an integrable function. It's assumed that x f of x is an integrable function. Okay, we have assumed here x f of x is an integrable function. Okay, and the whatever.
Yeah, but wait, so like this one thing. So like we have f of x times something that is bounded above by x square. So like where do we get?
No. We don't get. No. I'm taking square here. The square is less than or equal to this. So
sorry.
The integrand is bounded by x f of x, mod of x f of x. Okay, this is bounded by mod x of x. That's what I have said here. Then because I am taking mod, I squared it. Okay, so the integrand is bounded by x f of x. So which is integrable, we are assuming. So you apply Lebesgue dominated convergence theorem. You take the limit inside. If you take the limit inside f of x, this does not. I mean, it does not affect the f. It will only affect the other part, the e part. Okay, and there it is just differentiating e, which is just you will get e I xi x. Okay, that's what you will get. You will get e power I. I mean, you will get I xi, right? You will get I xi x. What will you get? Yeah, you will get I xi. You are differentiating the function I xi x, right? And you are differentiating with respect to x. So you will, I mean, here you are differentiating with respect to x basically. So you get I xi out, right? The constant will come out. If you differentiate it e power I c t, you will get the constant out when you take t. I mean, when you take t equals 0. Okay. Anyway, you check it. It's just ordinary differentiation. Okay. So this is about differentiation, and I said about integration also. Then there is something called convolution. Okay. That's we should be more careful about that. Okay. What is the number of this? 4, 2, 6. This is a product. See the L1, if you take two L1 function, f and g, then the product is not in L1. But there is something called convolution, which is in L1, which will again be in L1. So that is the right product on L1. Okay. So if you have fg in L1, so you define a product f convolved with g, which is defined like this. We will make sure this is well defined. Another thing, okay, f convolved with g at x equal to f of x minus y g of y dy, which is also equal to, by change of variable, which is also equal to g x minus y f of y dy. Okay. So this is what is called convolution. So we want to make sure this makes sense, and f star g is also in L1. That's what we want to do. Then we want to compute the Fourier transform of this. So that is our thing. The first thing is, so maybe I will write this as a proposition. So f star g. So first one is this. Okay, f star g x exists for almost all x in R with respect to Lebesgue measure. Okay, when we say almost, it is with respect to Lebesgue measure. Okay, and f star g is in L1 of R. Okay, further f star g, it's a single function, so its hat is equal to at xi. F hat of psi, it will become ordinary product. If you take the Fourier transform of convolution product, this is the ordinary product of the Fourier transform. Okay? So this is the proposition. Incidentally, the same thing till now, whatever I have talked, this is true in discrete series also, discrete Fourier series also. You have to the same technique, differentiation, integration, all those things, and then this convolution product. All these things work in the discrete series also. Okay? It's the same proof. Okay, now we want to consider this. So let us consider this function f of xy equal to, so what is the function? G of f of x minus y, g of y. Okay. So this is clearly measurable. Product of two function f is measurable, right? It's an exercise if you wish. I mean, the reason is we have proved that if you have, I mean, this map xy going to xy is measurable, and if f is measurable, g is measurable, then f of x, g of x, f of x comma g of x is measurable. You can use that if you want, or you can prove directly. We have proved all those things, I believe. So because of that, this is measurable. F is measurable, and the double integral f is measurable in R2. Okay, as a function on R2. Then you consider this f of xy mod dx dy over R. Now this is positive function, and we can use Stoneley's theorem. Okay, so we can compute this. So that is equal to integral over R2 f of x minus y g of y dx dy mod of this. So now let us first integrate with respect to dx. Yeah, first let us integrate with respect to dx. Then we know that by change of variable formula, it is same as the integral of, I mean, it's a single integral. I mean, no, you can substitute x minus y to be some z or something, which is, I mean, which is equal to integral over r, f of z dz. You can change the variable. Then mod g of y dy, right? Lebesgue measure is translation invariant, or you can use the usual calculus also. Lebesgue measure is translation invariant. So you get this. So this is equal to, is this okay? Yes, direct verification. Okay. So this implies f is in L1 of R2. So by Connelly's theorem, which says, which we have proved, this integral over R of f of xy, if you can take either dx or dy, whatever. Let us take dy. Exist. I mean, this exists. Yeah. This exists almost everywhere. That is, f star g exists almost everywhere, and f star g is an element. Both these things are true. That is the Connelly's theorem. If you have a two variable function, if you can integrate it, then if you fix one variable, then you fix one variable. No, you integrate with respect to one variable, then the integral, if you fix the other variable, then the integral exists in the other variable for almost everywhere. That's what the Connelly's theorem says. So from Connelly's theorem, we get this. Okay. Further, f star g, if you want to consider the integral of that, you want to compute the integral over R of mod f star g dx, which is equal to integral of mod of this f of x minus y, g of y, dy, then dx. That is less than or equal to integral over f of x minus y, g of y. We have a modulus inside dx dy, which is equal to, as we have done the computation earlier, which is equal to norm f1 norm g. So this implies norm of f star g L1 is less than or equal to norm f1 norm g. I mean, the reason for writing this inequality is what is, see, maybe a small digression just to tell you something. Even if we have the Banach space, if we have the, even if we have operators, if we have two operators, T, S in some B of some Banach space X, okay, then we have this norm Ts is less than or equal to norm T times norm S. This means that if you take some operator T, then you define a operator, some phi T from B of X to B of X, okay, where this S going to St or S going to Ts, whatever. These maps are these multiplication maps are bounded maps. That's what this inequality says. They are contractions. Okay, that's what this says. So similarly, we have already seen that if you, in the ordinary multiplication by multiplication by an multiplication operator is it's a bounded operator. Here this thing says that if you take L1 and you can multiply as a convolution operator on the left or right, and that is a bounded operator. That's what this says. Okay, that's why these inequalities are important. Okay, so we can either use this inequality here or. So any doubt, anything to ask till now? So what I have done is, we have two L1 function, then we have defined a multiplication on L1, which is the convolution of two function, and we have proved that the convolution exists. The convolution as a function exists almost everywhere, and that's what we want. We usually by L1 functions are almost everywhere defined. We need not.
Sir,
yes.
are we assuming F to be Borel measurable?
Yeah. When we say L1R, it's always Borel measurable.
Otherwise, it would may not be measurable with respect to product measure.
No. When we say L1 of R, something,
okay,
it is measurable function which are integrable. How do you integrate non-measurable function?
No, I'm thinking that you are using that BR2 equal to the product tensor of two BR and BR.
No, but the question is, when we say F is in L1 of R, F is Borel measurable.
Okay.
F is right. No, what is your question? You are asking
Borel measurable or Lebesgue measurable?
No, Borel measurable is enough. If you have two Borel measurable function, then the product is Borel measurable in the two variables.
That is correct.
Okay, that's right. So okay, so we have defined the convolution operator, and the convolution exists, and the convolution, the norm of the convolution f star g is less than or equal to norm f1 times norm g1. Okay, that is one thing. And so till we have done all these things. So finally, we want to do the following. We want to compute f star g. So that is only one thing remaining. Okay. So we want to prove f star g xi. We want to compute this, and that is equal to integral over r. Okay. Then integral over r f of x minus y g of y dy. Okay. Then we have outside, we have, so this is a function of x. I mean, this whole thing, whatever we have, the convolution, that's a function of x. I xi x dx, right? This is the Fourier transform of the convolution. Okay. Now we have I xi x, which we can take it inside, integral over r, and f of x minus y, we can write it as f of z. If you substitute z equal to x minus y, okay, then x equal to z plus y. So I xi z plus y, okay, g of y dx dy. Now you can see that this is just f of z e power I xi. You can see that that breaks into product. So this is just equal to f hat of xi to g hat of xi. You can see that e power I xi z plus y. So e power I xi z times e power I xi y. Okay. So you integrate one factor with the f, other factor with g, and you get this. Okay. That's all. So this is about convolution. Okay. The convolution is fine. It's clear. Is this fine? Someone says fine.
Yes, sir.
Then
Yes.
we just go ahead. Okay. So
Yes, sir.
okay. So we have so much time now. Oh, it has become 40 already. Oh my god. Okay. Finally there is something called Riemann-Leibniz lemma. So this, I think, Chaitanya gave some reasonable proof. Even though it's sketchy, it's clear. But as I have said, it's just in the L2 case. See, in the discrete case, f is in L1 of 0 to pi. Then we had f hat of n, which is nothing but, sorry, suppose f is in L2 of this, then f hat of n is nothing but f inner product with en, where en equal to en of t equal to e power int. Okay, which is just this integral. Then you can write in L2 as a function of L2. This is equal to f can be written as fen summation en. N is. So which is I mean, this does not point to its convergence. This is a this you can make sense in L2. And also we have that fen goes to 0 because it's a this f which is equal to f hat n. F hat n is in L2, small L2. Okay, and we have that this hat is a map from L2 0 to pi to L2. It's a unit. This is the L2 theory. Okay, I mean, we are just taking orthonormal basis. This En is just an orthonormal basis, so that's what happened. So this Fen goes to f hat n goes to 0 is what is called Riemann-Leibniz lemma in the discrete case. But it's I mean, but here we are saying, I mean, here it is true for a function in L2, but it is in general true for L1 function also. That's what the Riemann-Leibniz lemma. I think he gave a reasonable proof, so I will skip it. Now we will prove this Riemann-Leibniz lemma for the continuous case. for the continuous Fourier transform. Okay. So this is proposition. Even though it's called proposition, this is what is called Riemann lemma. So F is in L1 of R. Then what is limit F at psi. Now here also it's as mod n goes to infinity. I mean it's a two-sided sequence. It's a sequence indexed by integers. Goes to infinity. Mod n goes to infinity, no? So suppose G in L1 of R is differentiable. I mean, we usually have function which is almost everywhere defined, but sometimes we consider this as a function defined everywhere also. Suppose if you have a differentiable function and G supported, compactly supported. So that is G is 0, G restricted to K complement is 0 for some K contained in a compact. Outside a closed, finite closed interval, it is 0. Okay. Then we want to consider this G hat. Then what happens? Then so it is differentiable. Okay. Then G prime hat at psi, okay, which is equal to xg. We have already proved that this is equal to xgx hat at psi. Maybe there is a minus sign or somewhere. I think it's minus ix. No? Yeah, minus x. Okay. Now, since G is compactly supported, okay, and it is differentiable, this ix, this xgx is also in L1, right? Okay. Now, because of that, xgs hat exists, and we know that xgs hat of psi, its modulus is less than or equal to form of G prime. G prime. So xgx is a bounded function. So this implies G hat of xgx is bounded function. If you take, oh, sorry, it's I is I there. No? What do we have? I'm not using this. Sorry, I'm using the other one. You get I is I there. Sorry. No, there what I was referring was the differentiating the Fourier transform. Here G, this is I think I say this. This I didn't prove, but it's an exercise I left it. G hat of psi, right? Is this what I have done? Check, there may be a minus sign or something. Okay. Because of that, it will follow that Z hat psi. This is less than or equal to G prime of L1. One for all Z. Okay. Now this is a bounded function. This is a bounded function will imply, this implies that G hat psi goes to 0. Is this fine? I'm saying that you take a differentiable function which has support in a compact set, which is outside a closed interval, it is 0. Okay. Then you can take the Fourier transform of the derivative, which is given by I psi Z hat psi, and that's a bounded function. Okay. You had the Fourier transform, any L1 function is bounded function. Here G is different, G is differentiable, G is in L1, G prime is also in L1. Okay. I mean, you can integrate any continuous function on a bounded compact set. Okay. So because of that, the Fourier transform exists, and the Fourier transform is bounded. If you take any L1 function, its Fourier transform is bounded. So Z hat G hat Xi is bounded. So G hat Xi has to go to 0 if it has to be bounded. Correct? Xi goes to infinity, this has to go to 0, right? Okay. So we have proved, yeah. Ask.
Yeah, so repeat this please, like how the
okay.
this
So
step
I
came
have
about.
this fact. Okay. I'm saying that you take a function G in L1 of R, which is differentiable and has support in a compact set. Okay. So G has support in compact set, G prime exists, G prime is also integrable, G is also integrable. Okay. Any continuous function on a compact set is integrable. Now you take the Fourier transform of G prime, which is I psi G hat prime. Now Fourier transform of any L1 function is bounded. So I'm saying that Xi Z G hat Xi is bounded in Xi. So that implies G hat Xi has to go to 0. That's all. Right? That's all. This function x, f of x, is bounded means x goes to infinity, f of x has to go to 0. Right? Then only it will be bounded. Right? If it doesn't go to 0, it will not be bounded.
Yeah.
That's all. Okay. Now I have to use a fact which, see, the point is differentiable function with compact support is dense in L1. Okay, I really, so I use that fact. Okay, please assume this fact. Let me not go through. So, in fact, infinitely differentiable function with compact support itself is dense there. Or you can consider this. Okay, let me try this. You take e power minus x square. Okay, e power minus x square. So G times e power minus x. So you take the function e power minus x square. Okay, and truncate it. You truncate it smoothly. I'm saying the following. Let xi x chi x equal to e power minus x square on some what do you have? You have an L1. See, this is what you have. You have an L1 function. This is actually very easy to do that. Let me just give a oral sketch. You have a L1 function. Okay. So L1 function has to kind of die when it approaches infinity. Of course, when g of xi goes to 0, L1 function has to die. It has to go to 0 as xi goes to infinity. because it's L1. You are integrating L1 function. So you take a big interval. I mean, yes, you take. I mean, you take compact set. You take a K. Choose K contained in R compact. Okay, such that integral over K complement of mod f of x dx is less than epsilon, which you can do because it is L1. Okay, and there is a question asked in the exam, which also more or less says the same thing. Did I ask that question? You can find a set so that you can make this integral smaller than epsilon given a set. This is the continuity of the integral. Okay, so you can do this. Now on K, you take e power minus x square, and then you slowly, you smoothly take it to 0. I mean, after some small interval, you make it 0. And that's what you call that function as chi. Then you multiply chi with this g, then that will approximate this g up to epsilon. Okay. So this is what my statement is. Given epsilon greater than 0, choose g differentiable with compact support. I mean, outside a compact set is 0, such that L1 norm of f minus g1 norm is less than epsilon. This is possible. Okay. And I gave the oral proof that you take a compact set so that the integral outside the compact set of this f is less than epsilon. Then on that compact set, you define to be e power minus x square, and then smoothly take it to 0 within, I mean, maybe inside the, I mean, maybe you can take a smaller interval or something and then make it 0. When you multiply by that function, you will get that you get a nice function. No, that will not be differentiable. But I mean, that's not right. It only says it says compact support, but you want something to be infinitely differentiable. Is this true? I'm not sure this is true actually. Okay. I mean, in fact, infinitely different C infinity function with compact support is dense in L1. Anyway, let's forget about that. So using this, we can prove that. So how do you prove this? This is less than epsilon. Now you take f hat of g, f hat minus g hat. Okay. This is equal to f minus g hat, of course. So now we want to take the modulus. F hat z minus g hat z modulus of this equal to f minus g hat z. This is less than or equal to norm of f minus g, which is less than epsilon. Now g hat z mod goes to 0, goes to infinity. Okay. This implies lim sub of mod f hat z is less than epsilon for all epsilon. This implies limit of okay, this is fine. Except that this is differentiable function with compact support is dense in L1, everything is clear. Okay, it's fine. Any question? Okay. I mean, there is no question because it's clear, or you think there is no point in asking? Okay. So these things imply the following. So because vanishes at infinity. So what we have got is f is in L1 of R. Okay? Then f hat is a function in C0 of R. We have already proved it's uniformly continuous, it's bounded, and it vanishes at infinity. And this is a Banach space with infinity. Okay? And we have proved that f hat xi is less than or equal to norm f1. So this implies you take the supremum, f at infinity norm is less than or equal to f1. Okay. So Fourier transform is a contraction from L1 to C0. It's a contraction. Contraction means norm is less than 1. This implies the Fourier. I mean, if you define this Fourier transform from L1 to C0, which is f going to f hat, this is a linear map, and norm of the script f is less than or equal to 1. That's what this is. Okay. This is infinity. Okay. Okay. So why are we doing all this Fourier transform? Because we want to see this Fourier transform is a nice map, which is an injection, so that you can get back the original function by reversing you take the inverse Fourier transform. So the inverse Fourier transform is usually defined like this. If we have a f this, I mean, this is just formally I'm writing, because the C0 that may not be in L1. We want to ask something. F hat of x equal to f of xi e of I xi x dz. Okay. This is what is called inverse Fourier. See, you in the Fourier definition of Fourier transform, you had e power minus. Here you don't have the minus sign, you have plus sign. So this is what is called inverse Fourier transform. Now the question is, if you have a f in L1, how will you get back the f hat? I mean, sorry, if you have f in L1 and you know f hat, how will you get back that f from f hat? How will you get back that f from f hat? Okay, so that is this, whether this Fourier inverse Fourier transform, this formula is valid for f in L1. The point is the formula is not directly valid because this f may not be L1 integral. If you have a f, the f may not be L1 integral. But then we can multiply this f by some function. What is something called, for each epsilon, we can multiply this function. As epsilon goes to 0, this we will get back this function. So what I want to say is the following. Let me write this theorem, which is what is called Fourier inversion theorem. The Fourier inversion theorem is the following. Let f in L1 of R is continuous. So I think continuity is needed. Let's see. Okay. And f is in L1. And suppose, see, the point is this, suppose f hat is in L1 of R, okay, then f of x equal to, there will be a constant here. See, the point is, see, you should have said it initially. We are defining the Fourier transform like this. You have f and you have f hat is defined to be an integral like this. You can actually put a 1 by 2 pi. Usually, some people, when they define Fourier transform, they put a 1 by 2 pi. Or they don't put 1 by 2 pi, but then they will use this 1 by 2 pi in the inverse Fourier transform. Or you can put 1 by square root of 2 pi, so that you will get 1 by square root of 2 pi there, but there will be some confusion somewhere. So I am not putting any constant here, but there will be a constant somewhere. I think you will get 1 by 2 pi here. That depends on what is the Gaussian value. So I just put a constant here. Constant times integral over R f hat of xi e power I xi x d. So this is what is called Fourier inversion formula. But the point is, when f hat is not in L1, we cannot make sense of this integral. Okay, but we can still multiply by some function vanishing at infinities, like e power minus y square, e power minus x square, or something. Then we can integrate it. I mean, you have any continuous function, you multiply by e power minus x square, then you can integrate it. Okay? So proof. The proof I want to, this proof is actually direct. The Fourier inversion formula, when it is integrable, you just write the double integral. See, when you want to, whatever you have in the left hand side, which is a double integral. Okay. So when you just integrate it, you will actually get it back. So, but let us do this. This is usually proved using what is called an approximate identity. Okay. So let us take a function. We can take z of x equal to e power minus x square, or any function which vanishes at infinity or something. Okay, or you can take any other function also. That doesn't matter. Then I want to prove the following. Zero. Fat of maybe I could put z. We want to get that limit between z f of x equal to some constant times f of x. That's what we want. Yeah, this is my claim. Okay. So let us just calculate this integral. Limit epsilon goes to 0. Integral xi epsilon xi f xi dz 0. This is another integral. This is an integral. F of x e power minus I xi x, right? I xi x. Oh, f of f letter. So I xi x. Yeah, I xi x dx. Okay. And so sorry, this should be y. This is an integral, no? So it should be some y. E power I xi x. Y. Okay. That's right. Then dz. X is there. Right. Zero. Now we can take, so what do we take out? We can take f of y dy is there. We interchange the integral. We integrate with respect to that. So we get f of y here. Then we have this integral chi epsilon j. Okay. Then e power minus xi into x minus y, right? Xi I, I xi x minus y. There is a dy, sorry, it's dx, dz Okay. Is it okay? Yeah. I have not been integrating for several years now. Okay, so I might make mistake. I may make some mistake. So
It will be y minus
y minus x. X minus what?
I y minus x.
I is I y. Oh yeah, yeah. Because I put a minus sign here. Okay. We'll remove this. Is this fine?
Yes, sir.
Okay. Or I use I is I or whatever. Doesn't matter. I put a minus sign. Okay. So this should be fine. Okay. Now I want to make a substitution. So epsilon xi equal to some z. So integral of xi of some z. Okay. Xi that is equal to z. So this will become e. So what is that I'm substituting? Z equal to epsilon z. Okay. Z equal to epsilon z. That's the time. So xi equal to epsilon. So this is xi is z by epsilon. So that is right. So minus z y minus x by epsilon, right? That's right. Then there is dz. So but then dz equal to epsilon times here dz equal to epsilon will come down, no? I think this is fine. Okay? This is okay? Is this fine? I have just substituted z equal to epsilon xi. Okay?
Yeah. Yeah.
Yeah, this is fine. So
Yes, sir.
here it doesn't change. So here it is f of y as usual. Okay? Then xi z. So we have xi z. So I z I z x. So what if I want to take out the, yeah, this is just xi hat of y minus x by epsilon, no? Epsilon. And there is something by epsilon is also there. Right. Then there is dy by epsilon. Is it right? Okay. Now we substitute y minus x uh, by epsilon equal to some u. So this will become limit epsilon go to 0, integral f of, so then y equal to x plus epsilon u. Okay. And this is I hat of u, right? Then this epsilon, that epsilon will go. This is just u, right? Is this fine? But then we have assumed f is continuous. This is equal to, you get f of x out. The u will go away in the f. So this is just integral of I hat of u. Chi hat is a nice function, e power minus x square, which is an L1 function. So you can talk about chi hat. Okay. And I mean, you can take e power minus. See, the point is, you can work with this computer. I mean, why we take e power minus x square? Because if you take e power minus x square, the Fourier transform is also e power minus x square up to a constant. So e power minus x square is what is the Gaussian density function. Density function for the Gaussian probability distribution, if you know some probability. And if you take the Fourier transform of that, you get the same. See, the Fourier transform, if any Gaussian, is again e power minus x square. You just make the do the computation, do the integration, you will get that. Okay. So this exists. This chi hat of v exists, which is also again e power some. There will be a constant times that. Okay. So we got the f of x back by doing this. So that is what I said we want to do. Okay. I mean, I haven't assumed the integrability of f hat here. But if f hat is integrable, then you don't really need that. So here I want to make a nice statement. So I mean, I have made the statement like this. But then I'm using some sort of approximate identity. You just multiply by this is the statement I have to. The second, whatever in the bracket I have to. If this is confusing, you tell me. I will explain again. This is fine. I'm just saying we want to prove a Fourier inversion formula. You take a f, then you got an f hat. From f hat, by integrating, by taking the inverse Fourier transform, which is just integrating with respect to against e power I xi x, okay, you get f of x. But then for that, f hat has to be integrable. Okay, so this makes sense when f hat is integrable and other. So then you can do the same thing and you get the answer. I mean, that is just double integral. Just calculate the double integral. I'm saying instead you can, even when it is here, we are not assuming f hat to be integrable or something anywhere. Okay? So even when that is not the case, you can multiply this f hat by this nice Gaussian e power minus x square or something. Then you make it integrable. Then you have this following form. A Fourier inversion formula. So that is what we have to do. Okay. So it is 6:15. So the L2 theory, I will do it in the next class. Meanwhile, if you have any question, you ask me. Any question about this or anything else? Okay, shall I end?
Sir, when do we need to submit the assignment?
So I said next Friday. Shall we have it on next Friday? Week after that is exam, midterm exam. So it is weekend before that. Not tomorrow, next Friday.
Okay. Can you make it till that Sunday? Then I think that would be.
We have no problem, but you will have exams. You will be writing assignment till before the exam date. I think your
exam is on Thursday, right?
Huh?
Exam is on Thursday.
Our exam is Thursday. You will have some other exam, no, on Monday. So you want
no, I don't think there is any other exam. At least not for the.
I have no problem. You can submit it till even I can Sunday night I can. Okay, no problem.
Okay.
So I have to. I mean, I have to. You can submit it in Moodle, so I can. I will make a what is it program or file or whatever. Okay.
Okay.
Okay then. Bye. We will do the L2 theory in the next class.